In IoT networks, detecting and classifying both known and novel attacks poses significant challenges. Existing signature-based detection methods can be evaded by novel attacks, while anomaly detection systems often yield high false positive rates. Statistics-based and hybrid detection methods also have limitations, emphasizing the need for a more effective approach. To address these challenges, this research proposes a novel hybrid method combining deep learning with rule-based techniques. The proposed model classifies network traffic into three categories: normal, known attack, and novel attack. Leveraging the CICIDS 2017 dataset, which includes three new attack types unique to the training data, the model demonstrates its ability to recognize novel attacks. Deep learning techniques are employed to handle large volumes of network traffic data efficiently and accurately, reducing training time compared to traditional machine learning methods. The importance of identifying and classifying different levels of threats during automatic interactions between network devices is emphasized. The proposed method aims to handle these obstacles efficiently and identify various threat levels. Experimental results show that the proposed model achieves a good balance between attack detection, false positive rates, and false negative rates, with an accuracy of over 99% for novel attacks. The model utilizes a deep neural network architecture, specifically designed for handling high-dimensional network traffic data. By employing this framework, the model can efficiently process vast amounts of data, identify complex patterns, and classify attacks accurately. This approach has the potential to significantly enhance the security and privacy of IoT devices by accurately identifying and classifying various threats. The study introduces a novel end-to-end framework for detecting various types of attacks, including known and novel attacks, in Internet of Things, IoT, networks using machine learning. This approach aims to address the challenges posed by IoT traffic, which can compromise the performance and security of IoT devices. The contributions of this study include a novel framework for attack detection, achieving increased precision and reduced false positives and false negatives. This is attributed to the proposed tactic, requiring less time complexity compared to traditional machine learning algorithms, particularly when handling large amounts of network traffic. The proposed model's attack detection capabilities are illustrated in Figure 1, comparing its performance with existing intrusion detection systems, IDS. The network architecture of the proposed model is presented in Figures 2 and 3, demonstrating the strategy employed to protect the network from various novel attacks. The main objective of this work is to develop a deep learning-inspired, rule-based network security model that can detect and classify different categories of network attacks in various types of networks, including IoT networks. This model has the potential to address several security issues and attacks on different types of networks. By leveraging machine learning, this approach can detect and classify various types of attacks, including novel attacks that may not be detected by traditional IDS. The results presented in the figures demonstrate the effectiveness of the proposed model in detecting and classifying network attacks. Figure 1 shows a comparison of the proposed model with existing IDS, highlighting its improved performance. Figures 2 and 3 illustrate the network architecture of the proposed model, showcasing its strategy for protecting the network from various novel attacks. Overall, this study contributes to the development of a novel end-to-end framework for attack detection in IoT networks using machine learning. Its ability to detect and classify various types of attacks, including novel attacks, makes it a valuable addition to the field of network security. The proposed model's architecture and rule set are rooted in a comprehensive analysis of machine learning approaches for network attack detection. Extensive research has leveraged machine learning methods, including naive Bayes, quadratic discriminant analysis, QDA, and random forest, to detect network anomalies using datasets such as CICIDS 2017. Bekemla's study demonstrated that a multi-class classifier with an expanded feature set outperformed its counterparts. Marier's distributed deep belief network (DBN) feature reduction strategy and Pecta's integration of convolutional neural networks (CNN) and long short-term memory (LSTM) networks have also shown promise in enhancing attack detection performance. Recent studies have explored the application of deep learning algorithms for detecting and preventing malware attacks in cloud and IoT environments. Logistic regression and neural network classifiers have been employed to detect and prevent threats in smart IoT devices. A unique deep learning algorithm, LSTM, has been utilized for anomaly or redundancy detection and modifying attacks in IoT frameworks. Stackdeep polynomial learning-based intrusion detection frameworks, inspired by techniques such as spider-monkey optimization, SMO, have been designed to detect threats in IoT environments. LSTM, BILSTM, and gated recurrent unit (GRUP) techniques have been applied for binary classification of anomaly detection in IoT networks. A transfer learning autoencoder model has been introduced to detect noisy DDoS malware attacks, such as Mirai and Bashlight, in IoT devices, leveraging the CICIDS 2017 dataset for training and testing. The CICIDS 2017 dataset is a widely adopted benchmark for training and testing these models. The subsequent section will delve into the problem statement, defining the type of attacks and the dataset description, including the experimentation setup and results analysis. Deep learning and machine learning methods have significantly impacted anomaly detection and classification in various networks, including IoT environments, as demonstrated in previous studies. Building on these findings, a novel rule-based deep learning classifier model is proposed for anomaly detection and classification in networks, including IoT environments. This approach leverages historical network traffic data to classify inputs into three categories: normal, known attacks, and novel attacks, with high accuracy rates. The proposed framework consists of two stages. In the first stage, a deep learning model is applied to attack patterns from the training dataset to determine the probability distribution for each attack class. In the second stage, a rule-based model classifies the input sample into one of the three categories based on the probability distribution calculated in the first stage. The rule set for classification consists of three rules. Rule 1 classifies network traffic as normal if the probability of normal traffic is greater than or equal to 0.80. Rule 2 classifies network traffic as known attack if the ratio of the probability of a specific attack category to the sum of probabilities of all attack categories is greater than or equal to 0.80. And Rule 3 classifies network traffic as novel attack if the probability of normal traffic is less than 0.80, and the probability of each attack category is less than 0.80. The procedure for implementing the proposed model involves pre-processing the input dataset, splitting it into training and testing parts, applying the rule-based deep learning model to the training dataset, measuring the performance of the model, and then applying the trained model to unknown testing data to classify different categories of attacks. The CICIDS 2017 dataset is utilized for traffic data, and the performance of the model is evaluated using accuracy, recall, and false positive rate (FPR) measures. The importance of reliable datasets for machine learning systems is highlighted, citing the limitations of existing datasets, which can result in inconsistent performance ratings. The CICIDS 2017 dataset, released by the Canadian Institute for Network Security in 2017, is a comprehensive dataset containing benign and malicious network traffic data. Unlike other readily accessible datasets, which are often stale and unreliable, CICIDS 2017 offers a diverse and up-to-date collection of data, including 14 types of attacks such as DOS, DDoS, potato, brute force, web-based, heartbleed, infiltration, bot, and port scan attacks. The dataset contains a total of 7,469,090 records, with 78 features extracted from the network traffic, including destination ports, packet length, and flow duration. The dataset is segmented into three subsets: a training and testing dataset for deep learning models, a dataset for probability distribution calculation, and a sample dataset for novel attack detection. The training and testing dataset for deep learning models includes data from 4 attack categories: DOS, potato, web-based, and port scan, and normal traffic. This subset enables researchers to develop and evaluate their models effectively. The dataset for probability distribution calculation also includes data from the same 4 attack categories and normal traffic, with unique data points. The comprehensive feature set and diverse attack categories in the CICIDS 2017 dataset make it a valuable resource for research and development of intrusion detection systems. The inclusion of diverse attack categories and normal traffic makes the CICIDS 2017 dataset an ideal resource for developing and testing intrusion detection systems. The use of the CICIDS 2017 dataset enables researchers to evaluate their model's performance on a wide range of attack categories and normal traffic. This dataset is particularly useful for developing and testing intrusion detection systems, as it provides a reliable and comprehensive resource for research and development. Future work may involve exploring other datasets and developing more robust models for intrusion detection. However, the CICIDS 2017 dataset remains a valuable resource for research and development of intrusion detection systems due to its diversity and comprehensiveness. The proposed attack model for identifying novel cyber attacks utilizes a deep learning approach, leveraging the Python Keras library and TensorFlow backend, as depicted in Figure 7. This model aims to classify 4 distinct attack categories: DDoS, bot, heartbleed, and infiltration attacks, as shown in Figure 8. To evaluate the model's performance, the CICIDS 2017 dataset was used for both training and testing. The dataset was cleaned by removing records with NaN and infinite values, and feature normalization was applied to reduce the impact of outliers. One hot encoding was applied to the output variable to transform categorical values into vectors where only one element is non-zero. The dataset was split into training and test datasets in a 70-30 ratio, with the training dataset further divided into cross-validation and training datasets in an 80-20 ratio. The proposed deep neural network architecture consists of an input layer, several hidden layers, and an output layer. The input layer has 78 neurons, corresponding to the number of input features. 7 hidden layers were used, each with the ReLU activation function. The output layer has 5 neurons, representing the 4 attack categories and 1 normal category. The distribution of attack data in the training dataset is displayed in Figure 8, highlighting the importance of a balanced dataset for effective model training. The use of a deep learning approach in this model allows for the identification of novel attacks by learning complex patterns in network traffic. This research contributes to the development of more efficient and effective cyber attack detection systems. The deep learning model's architecture is designed to efficiently classify network traffic into 5 attack types: normal, DOS attack, probe, R2L, and U2R. The model utilizes the ReLU activation function, which facilitates quicker convergence due to its derivative properties, specifically, a fixed slope and zero derivative. The output layer consists of 5 neurons, matching the number of attack types in the training dataset, with the softmax function employed to assign decimal probabilities to each output class, ensuring a normalized probability distribution. The model employs cross-entropy as the cost function and ATOM as the optimizer, with a learning rate of 0.0001. The architecture is detailed in Table 8. Figures 9 and 10 illustrate the model's performance, demonstrating that after 150 epochs, the model's accuracy tends to stabilize, reaching a loss value of 0.0169 and an accuracy value of 0.9958 at 400 epochs. Tables 13 present the required maximum and minimum probability values for classifying network traffic as attack or normal, as well as specific attack types. Figure 11 displays the classification report, providing a comprehensive overview of the model's performance, highlighting its ability to accurately classify network traffic into various attack types. The model's architecture and performance metrics suggest that it is well suited for network traffic classification tasks. However, the choice of hyperparameters, such as the learning rate and number of epochs, may require further tuning to optimize performance. Additionally, the model's assumptions and limitations, such as the reliance on a specific dataset, may impact its generalizability to other network traffic classification tasks. A novel intrusion detection system, IDS, is evaluated for its effectiveness in detecting various types of network attacks, including normal, DOS, brute force, port scan, web attack, and the recently introduced potato assault. The ICIDS model's performance is assessed using probability values for each attack class, which are crucial in evaluating its accuracy in classifying network traffic. The evaluation metrics employed include recall, false negative ratio, and false positive ratio, FPR. Recall, calculated as the ratio of true positives, TP, to the sum of true positives and false negatives, FN, measures the model's ability to identify attacks accurately. FPR, calculated as the proportion of false positives, FP, to the sum of true positives and false positives, indicates the frequency of false alarms. A false positive occurs when the ICIDS mislabels permissible behavior as an attack, while a false negative occurs when it mistakenly classifies an attack as permissible behavior. The results, presented in Table 7, demonstrate the model's high accuracy in detecting various attack classes. For instance, the recall for DDoS attacks is 0.9934, indicating that the model accurately identifies almost all DDoS attacks. The FPR for DDoS attacks is 0.0221, suggesting a low rate of false alarms. Similarly, the recall and FPR values for bot, heartbleed, and infiltration attacks demonstrate the model's high detection accuracy. Overall, this research highlights the effectiveness of the proposed ICIDS model in accurately classifying different types of network traffic and detecting various attacks with high recall and low FPR, thereby contributing to the enhancement of network system security by improving the detection capabilities of ICIDS models. The proposed deep learning model architecture for network attack detection comprises an input layer with 78 neurons, 7 hidden layers featuring a ReLU activation function and a learning rate of 0.0001, and an output layer with a softmax activation function. The model employs cross-entropy loss and the atom optimizer, and is trained for 30 epochs. Performance evaluation results demonstrate a low false positive rate of less than 0.025 and a high true positive rate of more than 98.5%. The model achieves an overall accuracy of 99.5% and a recall rate of 99.9% across the 4 categories. Notably, it excels in classifying novel attacks, such as infiltration and heartbleed. A comparative analysis with existing approaches on the CICIDS 2017 dataset reveals that the proposed approach offers a more robust security mechanism, integrating rule-based approaches and deep learning algorithms. This synergy results in superior accuracy and speedup compared to traditional machine learning methods. The proposed anomaly detection system has diverse real-world applications, including health data anomaly detection, manufacturing fault detection, computer network intrusion detection, and predictive maintenance. Furthermore, it enables monitoring of various data sources, such as user logs, devices, networks, and servers. Machine learning and deep learning techniques have been increasingly applied to network intrusion detection and classification, with a growing focus on anomaly-based detection systems. These systems are crucial for identifying unknown security threats and zero-day attacks, which often evade traditional security methods. A proposed model combines deep learning and rule-based approaches to analyze network traffic patterns, detecting and categorizing various types of network attacks. The model's performance was evaluated using the CICIDS 2017 dataset, achieving an average accuracy rate of 99.5%, a recall rate of 99.9%, a low false positive rate of less than 0.025, and a high true positive rate of over 98.5%. Although the results are promising, the authors acknowledge that the CICIDS 2017 dataset may not provide sufficient reference points for the model to develop a comprehensive understanding of network traffic patterns. Future research directions include testing the proposed approach on diverse classes of network traffic, novel attacks, and evaluating the attack prediction capability of the model. To enhance the model's performance, the authors plan to convert raw traffic files into feature vectors using the IPFIX framework, creating a more comprehensive feature list. Additionally, they suggest applying recurrent neural network (RNN) and long short-term memory (LSTM) models to handle anomalies in time series IoT traffic data. These advancements could significantly improve the accuracy and robustness of network intrusion detection and classification systems. In the realm of anomaly detection and intrusion detection systems, a comprehensive literature review has been conducted on the application of deep learning and machine learning techniques in IoT networks and cloud computing. This review spans 36 research papers published between 2016 and 2023, encompassing various aspects such as network intrusion detection, port scan attempts, malware detection, and distributed abnormal behavior detection. The studies employ a diverse range of deep learning and machine learning algorithms, including deep belief networks, ensemble SVM, and recurrent neural networks. A significant portion of the research focuses on the utilization of deep learning methods for network anomaly detection and identification, with notable examples being the use of convolutional neural networks and autoencoders. Machine learning algorithms are also explored for IoT device identification and abnormal traffic detection. Transfer learning, rule-based probabilistic techniques, and simulation-based modeling for anomaly detection in IoT networks are other areas of investigation covered by the literature review. Furthermore, some papers delve into the design and development of deep learning-based models for anomaly detection in both IoT networks and cloud computing environments. This extensive review provides a thorough overview of the existing research in this domain, illustrating the growing interest and advancements in leveraging machine learning and deep learning techniques for anomaly detection and intrusion detection systems.